Good morning, everybody. My name is Kartik Nayak. I'm a PhD student at Università della Svizzera Italiana, which is located in Lugano, Switzerland. And as a part of EVEREST webinar series, I'll be speaking about the security challenges in distributed systems. This is the agenda for today. I'll be speaking about distributed systems. Then I'll move on to heterogeneous computing. I'll briefly speak about the security concerns. Then let's move to physical attacks and remote attacks. And I'll speak about the opportunities that the distributed or the heterogeneous computing model would provide for the efficient implementation of cryptography or other sort of security primitives. Distributed system is all around us. That is, if you take Google search engine or Amazon web servers, online banking to online gaming, all of them are distributed systems. So how can we officially or formally define them? It's nothing but a collection of separate or independent software and hardware components, which are usually referred to as nodes, that network together coherently by coordinating and communicating through events to produce one end goal. Here, the end user usually views this complete system as a single computer, and the complexities of the system are usually hidden from the end user to make the system look like a single computer in distributed systems, and which is one of the key aspects of distributed systems. Let me clarify that everything that looks like a client-server model, which is one of the most popular distributed systems, is not a distributed system, because if you have a client-server model that is running on a single computer, it cannot be a distributed system. For it to be called distributed system, it must have some characteristics. For example, heterogeneity and loose coupling. Heterogeneity is the presence of multiple computing elements of different sorts, and loose coupling is whether they can be easily plugged in or removed from the system. Then there shouldn't be a shared clock, that each computing element should have its own clock. And the state of the system is usually distributed throughout the system, and there shouldn't be any shared memory. That is, each process should have its own memory. The task should be independent and must be performed concurrently. And all these above characteristics must contribute to the dynamic nature of the distributed system. Distributed computing is a computing technique that is over the distributed system. And the basic notion of this computing system is the computational node. Usually, because distributed systems has a lot of heterogeneous nodes, they facilitate computational heterogeneity. Such computational heterogeneous, because of such computational model, can be also termed as a heterogeneous computing model. To speak about distributed transparency, it is facilitated by something called as middleware in a distributed system. And usually, the middleware is also responsible for making the system, the details of the system, hidden from the users who are performing their operations or who are querying the system for certain tasks. To do that, the middleware should perform the following tasks, that is the resource distribution and the task distribution over the resources. Then failure of resources must be handled by the middleware. Also the migration of operations from one to other resources when there is a failure of resource, or when there is an efficient resource that can perform the operation better, that is plugged into the system. So let's see the middleware. On the right-hand side here, I have 3 clients who are querying the middleware, and there are many nodes. I think on the slides there are only 4 nodes, but there can be many. And usually the middleware is the logical layer on top of these physical nodes, where the nodes themselves are hidden from the clients, as we have established this fact. And one of the aspects of middleware is that it should provide communication and security services. Also, the handling of the failure of the nodes is also done by the middleware. And also it manages the concurrency where the tasks are delegated to, if they are independent, they are delegated to two different nodes. So the middleware is responsible for creating the illusion of single computer. One thing we must ask as security researchers or computer researchers is that does it invite more malicious attacks, or does it produce some more leakage, or how do we identify if there is some failure of node? Is it a reliability issue or security issue? I think when we are providing the solution for things, it must answer all these questions. Let's talk about the heterogeneous computing. Here, on the right-hand side, I have the heterogeneous nodes that are used in the EVEREST project, where we have CPU-centric deployment and FPGA-centric deployment. You can see the CPU-centric deployment have, the internodes, if you see from the internode perspective, they are homogeneous, but the intranode, they are again heterogeneous because there is CPU and FPGA which are connected by PCIe Express bus. They together they can be called a node, which is connected to the data center network. On the other hand, we have FPGAs that are directly connected to the data center network. They are called network attached FPGAs. And then there is a CPU that can coordinate between these FPGAs, or the FPGAs can coordinate between themselves as well. And combine, the complete thing is obviously a heterogeneous computing architecture, because there are so many different computing elements combined together. Usually here, the operation to be performed on the node is instructed by the middleware, because middleware is very powerful. And also I would call the scheduling of the operation dynamic, because when there is a failure or when there is more concurrency that can be achieved, then there are new devices plugged in. Usually the scheduling has to be dynamic to cater to those needs. And such dynamic system should have security primitive that should adapt to this dynamic nature, which becomes challenging and also interesting. This is another view of viewing the same distributed computing nodes. That is, here we have a data center network, which is connected to a network attached FPGA. Then we have CPU, which is a Power9 CPU, which is connected to FPGA using OpenCAPI standard. And then there is an EVEREST node, which can be CPU, GPU, or FPGA, or the node can have all three elements also. And the setup can differ from one cloud service provider to the other cloud service provider, or CSP in short. There is an immense possibility how these resources can be grouped together, or what all resources can be had on the heterogeneous computing environment. Let's talk about the security concerns for the previous view that we saw. So traditionally, security is assumed to be, the security threat is assumed to be on the network, because most of the attacks happen on the network. So I think it's considered that traditionally, if you see, this data center network is the place where the adversary would look to inject some faults or eavesdrop, etc., which is not wrong, because most of the attacks are actually of the network infrastructure, but that's just a subset, I would say, although it forms a major portion of the attacks. Let's speak about the security vulnerabilities in the distributed computing, in the middleware, because it's too powerful. Firstly, I have interception, then interruption, modification, and fabrication. I mean, all the attacks on middleware can be divided into those four, and uh, they uh, they bring vulnerability to the security concepts such as confidentiality, integrity, and availability. For example, interception is an attack on confidentiality. Interruption, modification, fabrication can be an attack on both integrity and availability. Let me walk you through all these four in detail. Interception is the concept. The concept of interception refers to the situation that an unauthorized party has gained access to a service or data. The interception happens when data are illegally copied, for example, after breaking into person's private directory in a file system, or eavesdropping on phone calls, or reading emails, etc. This is an attack on confidentiality, as I've already said. Then interruption. Interruption refers to the situation in which the services or data become unavailable, unusable, destroyed, and so on. For example, denial of service is one of the it can happen because of the interruption. Then modification. Modification include intercepting and subsequently changing the transmitted data, tampering with database entries, and changing a program. Usually changing the file contents can be viewed as a modification. Here, usually the adversary knows what exactly to change. Then there is fabrication, which refers to the situation in which the additional data or activity that would normally not exist are generated. For example, this involves generating data, processes, communications, or some sort of activities. For example, if you send some message and that message has some sort of a virus or something that can be replicated multiple times and you get it as a spam, I mean, this can be viewed as creation of some sort of spurious data as well. Further, these threats themselves can be viewed as passive attacks or active attacks. Passive attack is usually where the unencrypted or weakly encrypted traffic are monitored for sensitive data or authentication information. A side channel attack is one of the most popular attacks, which is a passive attack. And in contrast, on inactive attack, the attacker usually bypasses the security system or breaks into the secured system, which is usually secured, and the attacks are mounted on the network backbone, or it can also be mounted on hardware directly. And this can be used on both integrity and the confidentiality as well. Here I have listed 4 of the popular attacks on distributed systems. There are many more attacks on distributed systems. These are the most popular ones. I'll walk you through those attacks. A distributed denial of service, or popularly known as DDoS attack, attempts to consume target's resources so that it cannot provide service. One way to classify DDoS attacks is in terms of the type of resources that is consumed. Broadly speaking, the resource consumed is either an internal host or on the target system, or data transmission capacity in the local network to which the target is directly attached or indirectly attached. In password attack, an attacker tries to crack passwords stored in a network account database or a password protected file. There are three major types of password attacks: a dictionary attack, a brute force attack, or it can also be a combination of both dictionary and brute force attack, which can be a hybrid sort of attack. And insertion of Trojan horse is a distributed attack where the adversary usually introduces code such as Trojan horse, uh, um, which can be distributed, which can later be distributed to many other companies or users. And distributed attacks usually focus on the malicious modifications of hardware or software at the factory or during distribution. These attacks introduce malicious code such as backdoor to a product to gain unauthorized access to information or to system function at a later date. Then there is a phishing attack. Usually, it's usually done by some sort of hacker where the hacker creates a fake website or a service that looks like an authentic service or a website that you want to use, but usually it's not, and you provide all your login information to such a service, and your authentication information is stored by the adversary to gain access to those confidential information. As you know that EVEREST is a data-driven architecture, that is, the data must hop between different nodes before the raw data is realized into a result. And there are multiple nodes it must pass through. Also, because we are interested in increasing the performance to power ratio, one of the aspects is distributing the tasks to specialized hardware that increases the communication between the hardware. So in such environment, the links must be protected against confidentiality and integrity attacks. And on the right hand side, I have shown how from data entry to data exit, all the links must be protected. Usually, traditional cryptographic guarantees can be used for protecting such links, but when you go for high performance computing using heterogeneous architecture, you use this architecture for some sort of benefits, which is mainly here performance to power ratio, and using a software implementation of cryptography between all the nodes may not guarantee such performance. So we believe at UZI that there is a scope for better security design. So what are the caveats while designing such the security systems in such heterogeneous or distributed computing architecture? For example, it should be possible for the sender of a message to know that the message was received by the intended receiver. It should be possible for the receiver of a message to know that the message was sent by a genuine sender. It should be possible for both the sender and the receiver of a message to be guaranteed that the contents of the message were not changed during while it was in transfer. For that, we have to identify methodology to access the security levels in a system, because here we're dealing with very different computational elements. Also, understanding the applications of middleware is very important. What sort of services does the user expect, etc. Also, we need to monitor the system security, which is very important in such a system. The security, for that, the security metrics must be properly developed and defined. And also the way the cryptographic techniques are integrated also form a backbone of the security systems. Now, let me talk about the key concepts of security. A fundamental concern is, before I speak about it, let me start with the first one, which is authentication. during authentication is a fundamental concern in building a secure distributed system. Uh, the authentication service is concerned with assuring that the communication is authentic. In the case of a single message, such as a warning or an alarm signal, the function of authentication service is to assure that the recipient that the message is from the source that it claims to be from. In the case of an ongoing interaction, such as the connection of a terminal to a host, two aspects are involved. First, at the time of connection initiation, the service assures that two entities are authentic. That is, each is the entity that it claims to be. Secondly, the service must assure that the connection is not interfered with within such a way that the third party can masquerade as one of the legitimate parties for the purpose of unauthorized transmission or reception. Speaking about access control, in the context of network security, access control is the ability to limit and control the access to host systems and applications via communication links and prevention of unauthorized use of resources. To achieve this, each entry to achieve this, each entry trying to gain access must be identified, authenticated, so that access rights can be tailored to a certain individual. Then confidentiality or data confidentiality is the protection of transmitted data from passive attacks and unauthorized disclosure. And integrity, just like the confidentiality, can be applied on stream of messages or a single message or selected fields within the messages. Again, the most useful and straightforward approach is total stream protection, a connection oriented integrity service, one that deals with the stream of messages, assures that the messages are received as sent with no duplication, insertion, modification, reordering, or replace. Then there is encryption, which is the use of mathematical algorithms to transform data into a form that is not readily illegible. The transformation and subsequent recovery of the data depend on an algorithm and encryption keys. Then digital signature is the data that is appended to or a cryptographic transformation of a data unit that allows a recipient of the message unit to prove that the source and integrity of the message unit and protect against forgery even by the recipient. Then we have non-repudiation, which prevents either sender or receiver from denying a transmitted message. Thus, when a message is sent, the receiver can prove that the alleged sender in fact sent the message. Similarly, also when a message is received, the sender can prove that the alleged receiver in fact received the message. Okay. While these key concepts can provide security guarantees against most of the attacks that we have, most of the attack protocols that we have discussed so far, there are also physical attacks that are on the fabric of the hardware directly, and they usually are more resistant to these guarantees. Let's see the physical attacks. As I told just now, physical attack is on the physical asset of the infrastructure that is usually on the CPU or some microcontroller or some FPGA, etc. And in heterogeneous computing, as we know that there are a lot of nodes, that is a lot of computational elements, and they are placed in different environments. So that probably gives more opportunities to come up with new um, um, new threat models or adversarial models, because the environment also plays a role, which we will see in short. Usually here on the physical, in the physical attack, the attacker or the adversary does not attack on the mathematical foundation or this. I mean, if I take the cryptographical example, usually the attack is not on the mathematical soundness of the cipher, but on the implementation. These are the three popular physical attacks. There is side channel attack, fault injection attack, and insertion of hardware trojans. We will see this in a very succinct manner in the next few slides. Firstly, the side channel attack, it's a passive attack. Usually it exploits the weaknesses in the implementation. For example, if I take the example of AES cipher, which is Advanced Encryption Standard, which is a symmetric cryptographical cipher, and which is mathematically very secure, and it can be implemented in software or hardware or on microcontroller. It can be run as well. Here, it's very difficult to break AES, even when the keys are 128-bit long. But using side channel, where the leakage can be measured in terms of power or timing, the AES can be broken and is broken. For example, using simple power analysis on a device that is running AES, you can understand that the device is performing AES, I mean, executing AES cipher and then running differential power analysis. You can also get the secret that it is, the secret key that it is using to encrypt the data. Then there is fault injection attacks, which is an active attack here. Usually the adversary tries to deliberately inject something into the system, and this can be in terms of voltage glitching, clock glitching, or laser injection also is a form of fault injection. Here the objective can be both an attack on integrity and also on the confidentiality. For example, there is a differential fault attack which can be performed at the end of 8th round on AES, which can get you the secret key as well. Also, this can be used as a denial of service attack, where you can inject something somewhere and the system will stop responding to the regular queries. And there is insertion of hardware Trojan, which is usually a malicious modification to the circuit that is fabricated. Usually, these are inserted in low controllability area, so it becomes very difficult for the semiconductor testing engineer to detect these circuits post fabrication if it's injected by the foundry. Inserted by the foundry. Also, if the hardware Trojans can also be inserted at a design time by some sort of IP provider or a CAD tool, or maybe even a rogue designer within the design company, and they can be activated based on some sort of timers or some state machines, etc. It can act as a backdoor, or it can just also lead to denial of service attack as well. Now let's talk about the remote attacks. I'll speak here about the remote FPGA attacks because in the EVEREST, FPGAs are one of the components that are used heavily to get the acceleration done for the machine learning applications, or from our side, even for the cryptographic implementations. When such FPGAs are used in in the cloud, the CSP usually gives them as infrastructure as a service or a platform as a service. So it's very common for them to give as a multi-tenant service rather than you having a FPGA for yourself. So when you give it as a multi-tenant service, this can open doors for a lot of remote attacks, which are physical attacks, but they are performed remotely. Before that, let's understand what multi-tenancy is. There are two sorts of multi-tenancies, that is temporal and spatial. In temporal multi-tenancy, usually the FPGA fabric is shared by multiple users at different time slots, or even the accelerators, as I mentioned on the slide. On the spatial multi-tenant FPGA, the FPGA fabric is usually divided into reconfigurable regions. For example, if you have 3 reconfigurable regions, at a time, 3 tenants can use the FPGA, and this is done usually by the CSP to maximize the utilization of FPGA and to reduce the and to increase the performance to power ratio. Here I have a CSP on the right-hand side, and there are 2 tenants, tenant A, tenant B, and there is a host, which is I would say, a controller or a processor where there are 2 processes running. A has 1 process, B has 1 process, and then there is FPGA. Say there is only 1 FPGA with 2 reconfigurable regions where A is running his code and B is running his code, or I mean, just there. They may just also be using some sort of code that is already present in there, etc. So here we see a total of 9 security concerns. The first one is the tenant data must be protected against malicious network adversaries when it is sent to the CSP. That is, I have, say I just want to perform a simple addition operation, and let's say some very complex addition operation where I send the same thing to the CSP because I'm lazy, and I'm tenant A. Then I have to send 2 operands to the CSP, that is to the host, and both these operands must be protected in transit when it's sent to the CSP. Then the second one is the tenant data must be protected against potentially compromised system software. Let's notch up a bit here, and let me say that I want to execute some sort of secret here on the cloud, and I mean I want those data to be protected when I'm sending them to the cloud. But you never know, you cannot trust the system software that comes with the CSP. I mean, whatever processor they have, the processor themselves, I assume, would have provided the system software, and your data must also be stolen by those or compromised by those system software, and it must be protected from the system software as well. And the third one is usually from the other tenant's workload. The other tenant can be malicious, and the tenant can also steal some of your data or inject some faults in your data to, you know, he might be, he or she or it, whatever, might be very malicious that want to stop you from executing certain operation, and he can just inject something that might not give you correct calculation or destroy the complete system, etc. Yeah, that must also be protected. Then the fourth one is the tenant data, which may be offloaded to the accelerator device, which is an FPGA here, must be protected when transmitted to and from FPGA. It's very straightforward. Which must be protected on the bus, because here mostly when we speak about this traffic is usually unencrypted. Then the fifth one is that the tenant data must be protected from untrusted or potentially malicious or compromised tenants executing on the FPGA devices, which is a new direction for research here. There are a lot of attacks now in this one where, I mean, in terms of fault attacks or side channel attacks where certain secrets are stolen from one reconfigurable region to the other reconfigurable, I mean, a certain secret from one reconfigurable region is stolen by a tenant in the other reconfigurable region. I mean, all of these are in research, but yeah, I mean, this is a possibility that we cannot ignore. Then in the case of disaggregation to distributed resources, the tenant data must be protected in transit. Again, it's same as usually the first one. Yeah, and whatever calculation that is performed must be protected when they are stored in some pools or a server. Then given the distributed nature of such resources, tenant data must also be protected at rest and in processing. Yeah, if you have stored it on servers, yeah, again, that must be protected. That's what it means here. Then the CSP must be able to trust the FPGA device provided by the FPGA vendor. That is, the FPGA vendor can also be malicious. That's what it means. And if you have, for example, the FPGA vendor may also insert some sort of ring oscillators, which can be activated at some certain points, and they can destroy the complete setup, that is the cloud service. I don't know why FPGA vendor would do that, but it's a possibility. Then enterprises hosting their own solutions and IP using CSP services must be protected. Yeah, if somebody provides some IP, for example, some sort of accelerator that's already present on the FPGA, or is it a part, I mean, it's stored on the FPGA, I mean, that must be protected. I mean, any information. I'm not saying that the complete IP can be stolen, but even to understand the part of IP is against the cryptographic guarantee, the security guarantees. So let's speak about the mitigation of attacks on multi-tenant FPGA now. The deployment of trusted execution environment, that is shortly referred to as TE, is used to isolate tenants, and OS can usually eradicate security concerns 2 and 3. For example, if you take Intel SGX or ARM TrustZone or something of this sort, even RISC-V has its own trusted execution environment. They should usually mitigate the security concerns 2 and 3 that we spoke about. Along the same line of trusting these hardware vendors for the TE architecture would also mitigate security concern 8. That is usually saying that some sort of security architecture for the FPGA, I mean, on the same line as CPUs should make us believe more in the FPGA developer, I mean, FPGA provider, the vendor, sorry, not the developer. And but that still doesn't address concern 4 and 5. Yeah, that's true. Then whatever IP protection that we usually provide for a standalone device should also hold in the cloud platform. And yeah, I mean, most of the IP theft countermeasures that are in research should ideally work in this setup as well. And as I've already established, the security 1 and 6 are network issues, and effectively implementing the cryptographic implementing the required cryptographic standards should address these issues. Security concern 7 has many solutions, but there is also a scope for further research in this direction. Yeah, when I say some non-physical attacks, these are all remote attacks. Usually the deployment of thousands of power viruses to construct a power-hungry circuit. Such attacks can crash FPGA, leading to DOS attacks. Again, these viruses are in terms of some usually they can be placed as ring oscillators, which can be uh, hardware Trojan that can be activated at some point and act as, I mean, that can act as a power virus and uh, destroy the FPGA. Also leveraging power-hungry circuit to induce timing failures during the operation of true random number generator used for the generation of secret keys. That is placing some, routing some wire next to the true random number generator can induce some faults in the random number generator. Not in the, I mean, as in the production of random number generator, and usually the secret key that is produced may not have the entropy that we desired from a random number generator. Then controlling the power hungry circuit to induce timing failures in the 9th round of soft AES 128 code to replicate the AES key recovery by means of differential fault attacks. This is the attack I had already spoken about. Such an attack can also be replicated in this setup. And then there is a voltage fluctuation sensors that can be used on the FPGA. I mean, that are used on the FPGA already, these voltage fluctuation sensors that can be exploited to gain the secret by processing the soft AES 122 or 128. This is a passive side channel attack, I think. Then exploiting the crosstalk effect between the long wires in FPGAs to successfully obtain the secret key on AES 128 core. Here, usually the long wire is placed next to an AES, a wire that is carrying the secret key. So usually when you place the long wire and connect it to ring oscillators on either side, usually there will be faults introduced in the secret key. So yeah, this is one of the other attacks. Again, as I have told before, there have been many other physically exploitable attacks that are known on remote FPGAs. In the previous slide, I just reported few of the attacks that were that I had gone through and I found important to bring it to notice. But yeah, there are many attacks known, and there are also many mitigation techniques known. But even having said that, there is a lot of scope for countermeasures, because there are more attacks than the countermeasure. Also, when there is a countermeasure, there is some other researcher who finds a flaw in that countermeasure, and that leads to a new attack which can be exploited. So let's speak about the EVEREST approach here. Usually the EVEREST approach is to simplify the implementation of big data applications using FPGAs or on FPGA platforms. And this is achieved through SDKs for the use cases such as traffic modeling or air quality control, etc. And using these SDKs, the programming models for the use cases are optimized for both CPU and GPU. However, everything is finally processed on CPU or GPU, or FPGA, and the attack oracle or the attack model, the threat model, they remain similar for such architectures as well, and that's where the security becomes more important. So in this project, we concentrate on the data integrity, basically, also, and we also concentrate on the confidentiality, but integrity is one of the important aspects in this project. We'll use some appropriate primitives there to provide some cryptographic strength. The implementations will be in terms of hardware mostly, or uh, um, um, also we will we are looking into different cryptographic primitives which can be suited for different applications or different scenarios. Also, we are providing some machine learning techniques to detect anomalies and how these techniques can be improved to be in the range of high performance computing. Let's see the opportunities now. While I have spoken a lot about the challenges, there are also opportunities that such heterogeneous computing model provides, because there are so many elements that are present in, computing elements or computing nodes that are present in heterogeneous computing, that you get this freedom to try your algorithms or cryptographic algorithms on different architectures and accelerate those operations, etc. Also, the cloud architecture can also be a doorway for fully homomorphic encryption, where the presence of different sorts of computational elements is a boon for homomorphic encryption, where we can try out or prove the relevance of homomorphic encryption in such setup. And we can also try out some sort of lightweight cryptography in the context of project, because they are usually very little resource consuming, and using it on some low computation, on a hardware that is much more efficient, can make it even better. Also, since we have FPGAs and few anomaly detection models rely on machine learning techniques, we can also exploit this possibility to accelerate the anomaly detection algorithms. Also, currently there are multiple works going on in the security for distributed systems. One of them is European Union project, where they leverage the task-based programming models to provide software ecosystem. And this is concentrated mostly on the energy efficiency, and it's named Legato. Then there is a SHA-1 collision detection cryptanalysis, which is in heterogeneous computing architecture. Then there is EDAC that offers single lightweight protocol, lightweight cryptography protocol for both authentication and key distribution in heterogeneous wireless sensor networks. Also, the current mitigation strategies also include RO-based sensors in the shell of multi-tenant FPGA to detect voltage fluctuation drop. I've told you before that ring oscillators are used as power-hungry viruses, but they also can be used for detecting the voltage drops and to locate the center of a power wasting logic. Then there are techniques where usually the netlist and bitstreams and things like that can be verified for potential power hungry viruses, but if you use it as a countermeasure, usually you must have some sort of understanding or rule in your verification where it must allow some ring oscillators to be a part of such a bit stream. But yeah, you must one must really understand where to place the ring oscillator and where not to place them. Then guarding of the wires is one of the other techniques which can be used for crosstalk effects, and using ROs as noise generators can also let's say minimize the leakage. I mean, they usually obfuscate the leakage. And then there are many more techniques that are already known, and then there are many more that are yet to come. As they say, more problems, more solutions, and that's the wheel that the research community relies on, where we find the problems in systems because it's important to fix them, and we find the solutions as well. So looking into this direction where there is a humongous opportunity for us computer engineering researchers to invest in new countermeasures, and also I believe that such techniques would give rise to an opportunity for security by design and for its momentum. Thank you.